We're now going to go back into the second of the four on technologies and talking about nuclear power. And I think during the renewables, you heard the start of some back and forth about how do we approach these things. It's not cut and dry, and I imagine that this is a subject that is also going to have that. So to moderate this panel, Mike Griffin of CMU, who has also been an amazing partner on the advisory committee leading up to this fact. So, Mike, thank you.
Good afternoon. I appreciate everybody showing up, but it's not really nice weather out there. I guess it took me about 45 minutes just to get in from Zealy and Opal this morning, sliding down 79. So I appreciate you showing up. I want to kick this off a little bit with reading a bio, because we had a replacement for one of our speakers, Jessica Lovering, who couldn't make it. And it's Amber Robson. She's a clean energy policy advisor for Third Way, where she works on nuclear energy and carbon capture and storage technologies. Prior to joining Third Way, she worked on clean energy policy with Environment Canada, Canada's Department of Environment and Greenhouse Gas Quantification expert for electricity, worked on electricity, oil and gas, and mining and manufacture sectors to inform their national climate policy. And later she worked on national regulations for industrial air pollutants such as SOx, NOx, and particulate matters, and focused on coal-fired power plants. Amber has a degree in chemical engineering from the University of Saskatchewan. I had a hard time saying that. And a master's in science from energy policy and climate at Johns Hopkins. So without going through an extensive bio for Mike, because you can read his in the program, but we were joking that we just had an admiral, and so Mike's got a high bar to jump over because he was only a captain. Okay, so Mike.
Thanks a lot, Mike, and thank you for PEC for hosting the event and inviting me to speak today. Much as Jesse did in the previous session on renewables, I'll try to kick it off here by presenting kind of a balanced view of what the role of nuclear may be or may not be in this whole question of decarbonization. The work that I do with, let's see if this is working here. I won't spend a lot of time first here talking about what Granger and Neil did a much better job than I could discussing what the initial focus is of the conference here, which is decarbonization. The question really is, though, unlike the discussion of renewables that we had late this morning, where there's a significant discussion of the level that renewables will play in the future for decarbonizing the energy sector, the question is a little bit different for the nuclear side, and that question is, will it play a role at all? And it's certainly one that's coming up on us fast and furious, not just here in the United States and in Pennsylvania, but around the world. And so I'll talk a little bit about that, and first by giving you a little bit of context. The section I want to talk about here, this is the Energy Information Agency's administration's view of what the grid mix is right now in the United States. And the section I want to talk about is the red section there, the nuclear part. Most of what we've talked about is decarbonizing and looking at the gas and the coal that certainly are carbon-emitting fossil generation that we're looking at replacing. The question is really, will nuclear's section of that remain the same? Will it get larger? Or will it shrink significantly, making that hurdle even greater than we currently have with just the coal and the gas emissions that you see from the prior speakers? Stepping back just a little bit to talk a little bit about Pennsylvania. Most of you should know that Pennsylvania is one of the largest electricity producers in the country, one of the top three, and is the second largest producer of nuclear energy behind Illinois. It's a little bit larger mix than what you saw in the last slide that I just gave to you. It's one of the, it is the first state in nuclear, and with a plant that was developed in 1957 at Shippingport and operated for about 25 years. and it also is famous for having the worst nuclear incident in the United States as well, at 3 Mile Island. So it's got the good side and certainly got the downside when it comes to nuclear power in the United States. The other thing we know is that natural gas is certainly on the rise in Pennsylvania. It's been mentioned previously here today, and coal is on the decline somewhat. And you can see that here on this slide, indicating that unlike other states that have nuclear, it's a very large proportion of nuclear in the state of Pennsylvania, but natural gas is catching up quickly as it replaces aging coal plants. Renewables are not a significant portion of the mix in Pennsylvania at this point, although there has been significant wind growth, and there are good goals that are certainly out there for renewable penetration in the state of Pennsylvania by 2021. I think the last thing I'd read was about 18% was one of the goals that they had for penetration for renewable power in the state. That nuclear contribution is made up of 9 plants at 5 sites. There is still a plant operating at 3 Mile Island, and then the other 4 sites. These are generating at fairly high capacity factors, so all are working very well and producing low carbon energy to the grid. And and so what happens is between Pennsylvania and the other states, these plants provide a significant portion of the low carbon energy within the United States, to the extent that the Energy Information Administration sees them as being a part of the mix all the way out into 2040. And if you saw the scale that there was in the original one of these I showed, that 19 to 20% mix of nuclear stays that way out till 2040. The question I want to talk about a little bit today is that a realistic assumption? Is this something that we should expect? What are the limitations and challenges that nuclear faces to maintain that, that mix of the grid? And what are the opportunities it might have to expand it? Or is there enough uncertainty in the cost and some other issues related to nuclear technology that it's going to shrink significantly? The benefits of nuclear are fairly obvious for most of the people who are familiar with it. It's over 60%, if you looked at the original slides there, of the low carbon generation in the United States. It's got about a 90% and sometimes higher capacity factor, meaning of the maximum amount of time it could be on during the year. It almost always is. It's got few constraints on the fuel supply, unlike coal and natural gas at times, especially if you're familiar with what happened in the Northeast during the polar vortex. Significant impacts from gas availability and coal deliveries. And so nuclear carried the lion's share of the grid for a significant period of time during the polar vortex a number of years ago. It's got significant improvements in operational safety and certainly in availability over the last 30 years. There was a time when that 90% capacity factor was in the 50 to 65% for quite a few of the plants, and that's increased significantly, making it a significant generator most of the time in the United States. It's got a low land footprint as opposed to some of the other potential impacts that you might have from a deeper wind and solar penetration, and significant contributions to grid stability and inertia, something that we've not really talked about here today, but certainly quality of power can matter just as much as quantity of power, and having those strong baseload generators with significantly large generators operating full on can have a significant impact on the reliability of the grid. It's also got a high economic impact, and some of my colleagues at Carnegie Mellon have looked at this compared to other areas of the country that have generating stations near them. Typically, the economic performance and tax base is much improved by having a nuclear power plant somewhere near them. So, why aren't we building more of them? Well, the challenges are pretty extensive, and this is by no means a complete list of the challenges that nuclear faces around the country and around the world. It's got significant cost risk to it for most developers. Anybody that's been familiar and watching what's going on in the 4 that are being built in the southeast United States at Summer and Vogtle know that there have been schedule overruns, cost overruns. And in fact, the last I saw in the Summer plant was they may eat up the entire 18-month buffer they put in on the right side for their schedule. So when they were originally scheduled, add 18 months at least right now for them to come online. The model for development is an old one. It's what I call the civil engineering project base versus production of a product. And so it's very much fraught with risk for development. If you look at the actual costs of development, most of them are in the site preparation, 50 to 60% of them in previous studies. And so if you have problems with concrete pours or anything like that, it can significantly slow the progress in development. There are long-term waste management issues. I'll talk about that in a little bit more detail here in a second. Fuel cycle issues related to proliferation risk. Safety and security. Since 9/11, there have been concerns about safety and security and the security of nuclear power plants, and so the costs that are borne by the power plants for security are taking up a larger share of their annual operating costs as we go along. There's also stagnant development, and Grainger talked about this in some of my research. We've looked at development of plants that might be cheaper to build, things that are advanced designs that are not light water, which are the current generation of plants that we have now, things that might be lower cost because they don't involve high pressure systems that take these huge pressure vessels that take a significant amount of money to build. But those are unknowns, and the amount of money being spent by the U.S. government certainly, and certainly by industry, means that the likelihood that they're going to be available in the near term to help with our decarbonization of the energy sector is very low. We've done a significant study of the budget for research and development for advanced nuclear designs for the Office of Nuclear Energy, and it's by far too low. If we think it's going to take $5 to $6 billion of government expenditure and about the same amount for private expenditure to get one technology ready to go in the next 10 or 15 years. Over the last 20 years, the Department of Energy has only spent $2 billion combined for all the research into advanced plants. There's also a rigid regulatory model and one that's only really designed for light water plants now. Now, there's been some significant work here, and I don't see Armand Cohen in the audience here, but Clean Air Task Force and a number of other organizations have done great work trying to move forward on a regulatory model that will help advanced designs, if they do become available, get through that regulatory process, which is a significant hurdle in the United States. And finally, poor public perception is a significant issue, and it still is, and this is pretty rigidly entrained. Grainger could probably tell stories that he has talked to us about in classes at Carnegie Mellon, looking at how heavily entrained this bad public perception is of nuclear power. Just a little bit more detail of some of those challenges that I mentioned. If we look at costs, the construction delays and increasing capital costs are a significant problem. If you've read the problems that Westinghouse, Toshiba company, is having recently, they've had significant write-offs financially. We've also had market issues, and while we've seen some relief in New York and Illinois that have kept some of those plants viable economically, other states are going to face those problems in the future for the plants for their operating costs. Plus, there's a significant, if you see that tall peak there, that was the peak of build back in the 70s and 80s for nuclear power plants worldwide. Well, as I'll show later, a lot of that is now going to be coming to the point of decommissioning in the next 30 years, and that's going to be a significant unknown for cost in the future. I'll also note that with, kudos to the economist who put this graph out, that of the 55 plants that are being built around the world right now, 35 of them are behind schedule. So Steve Brick mentioned earlier having a good business case for people to want to invest in a technology. Well, nuclear's got that problem, and it's had that problem for quite a long time. Other challenges, and I won't spend too much time on this because I think Matt McKinzie will hit on this a little bit more, but waste has been a continuing issue for nuclear power in the United States. Yucca Mountain has basically been frozen in place for years, and even to the point where a federal court allowed utilities to stop making payments to make it viable because it was so frozen in place for the political process. Storage is not just a U.S. issue. There's been some discussion about further development, whether it's small modular or otherwise around the world, and some of the storage facilities for spent fuel could run into capacity problems worldwide if there's greater deployment worldwide as well. There's a continuing debate about the fuel cycle. I won't get into that here since I wasn't asked to talk about it, but closed fuel cycle would mean perhaps reprocessing of some of the spent fuel, which would limit the amount that you'd have to put in storage, but that also brings with it increased security concerns. And right now, the prevailing opinion, I think, in policy circles for the U.S. is that it's not necessary based on fuel availability and what the actual volume of storage is that you have to worry about in the future. Finally, We still have some poor work practices that worldwide that need to be looked at for mining for uranium, so those need to get addressed, as well as limited capacity for new fuel. If we decide to go down a new fuel path, whether it's a trisul fuel particle or things like that, some of the development capacity in the United States, if we were to expand nuclear, would be challenged based on fuel development in this country. Some things don't take words. And so public perception, whether it's from Godzilla to Homer Simpson to the China syndrome back in the 70s, the public's perception of nuclear power has been pretty one-sided, if you will, and that's despite the fact that the reality of nuclear power safety, if you compare it, and Jesse would caution us about doing apples to apples comparison, but certainly if you compare it to other generating technologies and the safety involved in that technology and the impact it has on a death per terawatt hour scale, then nuclear is extraordinarily safe. And I will note, just to be fair to the renewables crowd here, if there are some of that in that group, that the rooftop solar, even though it shows higher, those are people falling off roofs installing solar panels. Those aren't the technology itself causing problems. This work actually incorporated all the deaths that are associated with it, whether it be in construction, emissions, et cetera. So for over 16,000 reactor years of operation, only 3 major incidents, very few deaths. And so when you do it on a scales perspective, the real message is it's fairly low. And there was even a very good article I'd recommend to you in Risk Analysis recently showing that societal risk for nuclear power is actually extremely low by a lot of different measures. So why, however, if nuclear's got all these problems, why are we still even talking about it? Well, with compliments to my friends at XKCD, it's got a massive fuel energy density. It's one of those technologies that we've been operating for about 60 years. A lot of it we know. We understand some of the complexities of it. And so there are a lot of knowns, all right? And one of the big knowns is it's just got this massive power capability, and we want to be able to advantage it and use it to our advantage in the energy system. So there are some bright spots. And the economics may be able to work out if we do some standardization of design. The UAE has certainly shown that they can build large-scale plants in quantity. They've got their 4 plants are on on schedule and on cost right now. There have been some benefits to the market that have been pushed forward by New York and Illinois. The waste issue, while the waste isolation pilot plant in New Mexico was closed for a while, it recently reopened. That's not going to solve the commercial nuclear issue because that's for waste from weapons development. But we may learn some things from that, and that might help us move forward on the commercial side. There's some congressional support that's out there, thanks to a lot of work by a lot of organizations to move forward with advancing nuclear technology. Most recent being the Nuclear Energy Innovation and Modernization Act. That we'll see if there's much money put against it. But certainly there's some congressional support out there. And finally, there's a significantly different landscape out there for developers. And so a lot of new companies, a lot of startups are out there, and some additional money has been put in that's now looking at different designs, and in some cases looking at things that are old that are now become new again, whether it's a sodium cool fast reactor or a high temperature gas reactor or molten salt reactors. Those technologies are being re-examined, even though they were designed and in some cases built back in the 60s. They're now looking at them with better computing power and better materials research. They may become more viable. And they're even looking at different deployment models. The upper left portion there is the MIT design for a floating nuclear power plant that would go off the coast. But the big thing I'd note is that much of this development is not in the United States. While the technical skill and a lot of the original designs and the technical understanding of some of these was from our national labs and was from the United States, the people who are actually forwarding the technology and building the technology are not in the United States. The vast majority of it, if you saw from that economist slide, is not here. Only 4 major plants with NuScale going to build their SMR in the Idaho National Lab in the coming years. assuming they get through the licensing process. So, what does that all mean? Well, here's the concern. If some of these problems are not fixed, will that red bar shrink significantly? And this still shows this scenario is basically replacement of nuclear, no replacement of nuclear with other nuclear, and plants starting to age out in the 2030 to 2050 timeframe. This still shows the expansion of renewable energy that we expect. What's going to fill that hole? Well, more than likely, that blue bar will significantly grow because that's the lowest cost thing to build in the United States. And so the problem that we face is what happens? Well, clean power plant's probably not a great comparative model right now because I'm not sure what the viability is of the clean power plant these days. But some analysts at Carnegie Mellon took a look at what would happen if you replaced all of the nuclear with natural gas combined cycle. What would happen? Well, as you can see, the 2030 scenario for total clean power plant reduction in carbon emissions would almost be wiped out legally under the Clean Power Plan by replacement with natural gas combined cycle, because you can replace it as long as the plant that you replace it with meets the standards, and the natural gas combined cycle do. And so it's even more telling if you look at Pennsylvania, where because it has such a high proportion of nuclear power plants, the goal that it was set for Pennsylvania under the Clean Power Plan would be more than wiped out, and you would actually have higher emissions if you replaced the nuclear power plants in this state with natural gas combined cycle. So obviously there are significant challenges out there. And just to say that it's not something that's speculative, it's already happening in the United States. On the left are the 4 plants that were closed in 2013 and 2014 before they reached the end of their service life. And on the right is the entire solar generation for 2015. So those 4 plants, decommissioning early, wiped out that much clean energy. When Diablo Canyon goes away, essentially over 20% of the clean energy that's out there already in California. So what will be going on? Well, the prior panelists would probably say, well, that's going to be replaced by energy efficiency and renewables in a lot of cases. Yes, but not entirely. And what that means is that in 2024, 2025, what you're going to have is you will spend all this time over the next 10 years basically replacing already clean energy with the new penetration, right? You're going to be just playing catch up. And for something that you know could stay around longer and be low carbon, you're going to be playing catch up and not making any significant gains. And as Granger and Neil pointed out, we need to be making gains. We need to be making reductions. We can't be fighting, and it's not just in the United States, it's worldwide. The high marks you see there are the maximum capacity for those countries for nuclear generation, and you'll note that virtually all of them are below that now. And all those plants, mirroring that slide that I showed you of construction, are now starting to age out as they're now at an average age of 29 years. Pennsylvania is no different, with an average age of reactors of about 35 years. The last detail, and I couldn't get full detail on this, but 2 of them didn't show as having 60-year licenses, but I suspect that they will have. But is there a chance they'll go to 80 years? Not sure. Some of the materials concerns might drive them to not want to extend the licenses, and especially if the cost side doesn't play out for them operationally. So near-term decisions are needed for Pennsylvania on what to do with that significant portion of the generation that is now attributed and is clean from nuclear power. New designs have good enhancements of safety. They may be able to play in not just nuclear electricity generation, but in other aspects of the energy system, whether it's industrial uses. And I'll just say that small modular designs may have some benefit in that, and we're going to be taking a look at that at Carnegie Mellon. In Pennsylvania, certainly all the coal plants could be replaced, or some portion of them could be, rather than just all renewables. Some of them could be replaced with nuclear generation. And the chart on the bottom is from a recent NREL and INL study that looked at industrial loads. And you can see a concentration, if you can squint that far, in industrial loads in Pennsylvania that use fossil generation right now and use heat loads that it may be possible for nuclear to take a role in. So what is the future? Well, we asked that for some experts last year. And we said, what happens if we don't make any changes in the way we innovate and the way we develop nuclear power? And the answer was pretty telling. They all saw a gradual decline in nuclear power over the next 50 years, to the point where it would be a very small contributor to clean energy in the United States. We then gave them what I would call somewhat of a blue sky proposal and said, what if we devoted ourselves to a clean energy economy and improved the ability for a regulatory process for new designs to get through? Well, they all saw a significant rise, but you'll notice the massive spread in uncertainty. Before, there was a very certain degradation in supply. Here, it's anywhere from 5% to 75%, and so essentially unknown. So the future of nuclear is certainly uncertain in the United States and certainly in Pennsylvania. But I would posit that the ends ought to be the focus, not the means. We talked about renewables and what portion they might share. But I'm of the same camp of Steve Brick and Jesse Jenkins, and that is that it ought to be an all-of-the-above approach. There ought to be a discussion of not the means, but the end, and the end is a decarbonized energy sector. Nuclear can possibly play a role. We ought to be looking for synergies where nuclear can really play and not battles. I'm a former military person, and so I believe in defense in depth. I believe in having not all the same kind of platform, so don't just give me the battle with one destroyer. I'd like to have an aircraft carrier and a cruiser and a couple of other things to go fight that battle with. And the enemy is carbon emissions, not one type of technology or one means and not another. But I would also say that nuclear has to address some of its concerns if it's going to play a role. Because if it can't fix the cost issue, and as Steve Brick would say, if you can't make the economic case for it, then it becomes challenging for it to compete. Thank you.
There we go. Okay. Thanks a lot, Mike, and thanks for having me here today. It's great to be a part of this really important conversation. As you know, I'm a clean energy policy advisor with Third Way. We are a small think tank based in Washington, D.C. We're a centrist think tank, and we cover a broad range of issues, including energy and climate. And we come at this issue with our interest to finding a solution to climate change. So I'm here to present today the pro-nuclear side of the debate, and whether nuclear is key to successfully tackling deep decarbonization. And I'll just say up front that for myself and for my organization, we don't believe there's a silver bullet technology. We think that this challenge is big enough that we're going to need all of the low carbon technologies, and those views are similarly in line with Jesse Jenkins and what Mike said just now. So we really believe that nuclear is going to play a very important role, but that it is not the most important answer out there. We all know deep decarbonization is going to be a really big challenge, and there are many ways to characterize that. This is one way that I've characterized that challenge, is to look at how much low carbon generation are we going to need in a deep decarbonized scenario. So I looked at two studies, the Deep Decarbonization Pathways Project and the United States Mid-Century Strategy Benchmark Scenario. And between those two sort of benchmark scenarios, we needed somewhere between 7,000 and 8,000 terawatt hours of low carbon electricity generation in 2050. And that orange line in the middle there is our current electricity generation, somewhere around 4,000 terawatt hours. So after we electrify industry and buildings and transportation, and we account for efficiency, we have a near doubling of our electricity generation. So to put that in context, the next small green line there is our current low carbon generation. This includes our nuclear, our hydro, and our renewables. So basically, to get to our 2050 goal, we're going to need to multiply our current low carbon generation 5 to 6 times. So this is just to make the point that this is going to be a huge challenge, and we need to do this in the next 30 to 40 years. When we look at the current rate of wind and solar additions, we see the next two lines there. The last one just doesn't even register. it's just not moving fast enough. We need to start adding low carbon generation as fast as we can for the least cost. So we believe that including nuclear in that mix is going to make that goal more achievable, and it's going to make that goal less expensive. So this is consistent with what most deep decarbonization research is showing. The IPCC, of course, is calling for a tripling to quadrupling of all technologies, including nuclear. The Deep Decarbonization Pathways Project included nuclear in its scenarios. It also found that the high nuclear scenario in its modeling was actually the lowest cost scenario. The United States Mid-Century Strategy, prepared by the Obama administration and submitted to the UNFCCC last November to outline how we can reach our 2050 goals, actually included nuclear in all of its scenarios. This shows 4 of those scenarios. It shows the final electricity generating mix. And so you can see the top there, the gray and the yellow, is wind and solar contribution, and the orange is nuclear's final contribution in many different scenarios. So nuclear is making a steady and significant contribution in these modeling scenarios. And when you take a technology off the table, the third bar, moving to the right there, shows that the nuclear contribution actually increases. And again, sort of looking at the benchmark scenario here, this scenario is calling for an increase of 60% over our current nuclear capacity in order to meet our 2050 goals. So that is quite significant. And there are many other studies out there that come to the same conclusion. When you take nuclear out of the mix, reaching the goal becomes harder and it becomes more expensive. And this is something that is kind of counterintuitive, and it's actually something that Jesse talked about quite a bit this morning. And it's that the upfront cost of a technology isn't telling you the whole story of what that technology does in the energy system. So nuclear actually brings a lot of value to the electricity system, and it brings a lot of value to deep decarbonization. So nuclear, of course, is a very reliable, always-on base load technology. So we don't need to build extra capacity or have some backup energy sources when we put nuclear on the grid. And so this makes it a really important, as we call it, base load source of energy. But in addition to that, looking at deep decarbonization scenarios, we're going to have, no doubt, growing penetrations of intermittent renewable energy, which is going to create demand for flexible generation sources on the grid. And nuclear, both existing, has some potential to flex to balance those intermittent renewables, and advanced nuclear sources is going to have an enormous potential to act as a flexible source, low carbon source of energy on the grid. And there's other areas where nuclear can help as well. Mike mentioned industry. Industry is our third largest source of greenhouse gas emissions, and there currently aren't a lot of solutions being discussed for how we can decarbonize this sector. Process heat is one of the biggest greenhouse gas emission sources, and advanced nuclear systems and existing nuclear systems both can contribute by providing low carbon process heat. So the key here, we think, is looking at this problem from a systems perspective and looking at the needs of the grid and how different technologies can work together to find the most cost-effective and the most resource-effective way of meeting those goals. Excuse me. So where do we start? Mike talked a little bit about the existing nuclear fleet and the challenges that it's facing due to low natural gas prices and cheap renewable resources. This existing nuclear fleet is actually currently our largest source of low carbon energy and is also our most cost-effective form of low carbon energy. Maintaining these units is actually more cost-effective than building new sources of wind or solar generation. And what history has shown us is that when an existing nuclear plant closes, greenhouse gas emissions go up. And this is a diagram from the Energy Information Administration, which shows 4 recent closures. And the energy generation mix 12 months before the closure and 12 months after. The yellow in there is nuclear, the brown is not, or the light brown is natural gas, and the dark brown is coal. So in the case of Crystal River, 12 months after the closure, natural gas increased, emissions went up. Same thing for San Onofre, natural gas increased significantly, increasing the state emissions 24%, et cetera, for Wisconsin and Vermont Yankee. So, you know, we do currently have proposals on the table to replace, again, as Mike mentioned, Diablo Canyon with efficiency in renewables. And if that is achieved, I'm not sure that that is a success, because we've gone and invested a significant amount of resources to end up where we started. So we think that we need to make sure that we're investing our resources to be adding low carbon sources of generation on the grid. So the clean energy standards proposed by New York and Illinois set a really good example, I think, of how to move forward with the existing fleet. So next, if nuclear is going to make a continued and growing contribution to a deep decarbonized system, the sector is going to need to address some of these many challenges that it's facing, which Mike mentioned, related to cost, related to public perception, related to safety and waste. So fortunately, there's more than 50 private sector interests out there working very hard and diligently to do just that. These entrepreneurs are looking at a variety of advanced nuclear designs for a variety of applications, and with the intent to address many of these challenges. So it's a bit complicated. I won't go into details, but I'll just sort of point out high level what are some of these key changes that are really going to make a big difference. So first of all, one of the big differences is that we're looking at smaller reactor designs. So instead of the larger 800, 900,000 megawatt reactors, we're looking at micro reactors and small modular reactors that range from 10 to 300 megawatts. So this has important implications on the costs of construction, but it also has important implications on sort of the business case for these reactors and what are the possible applications for them. In addition, they're looking at using alternative coolants aside from traditional light water. We're looking at molten salt reactors, sodium-cooled reactors, helium gas. But the important thing about the coolant is that it makes a major change in the design of the reactor. Takes out the need to be operating in a pressurized environment, therefore reduces the amount of materials required to build a reactor, thereby reducing the total overall cost. Simplifying these designs also will simplify the construction process. So, you know, construction is a great part of the cost overruns for nuclear right now. So these designs are hoping to address that. And with the possibility of being able to fabricate these designs in a factory setting, we're opening up the opportunity to deploy these units a lot faster than we are currently deploying nuclear technology. So most importantly, these advanced nuclear designs will have passive safety features, and this means that you know, electricity or human intervention isn't required to trigger the safety mechanisms of these reactors. So many of them are described to be meltdown proof. So these are just a few of the potential features of the advanced nuclear reactor. We think they have huge opportunity to be a part of deep decarbonization because of their potential for lower cost, their potential to be deployed rapidly, to act as a flexible low carbon resource for grid balancing, to provide remote low carbon energy to decarbonize industry, to go on and on. So they offer a lot of value. Our work at Third Way is focused on sort of supporting this innovation cycle so that we can make sure that some of these reactor designs make it to the finish line and are commercialized, hopefully, in the near future. So that is everything that I was going to say. Our sort of final message is that we think that we do need a mix to tackle this problem, but by including nuclear energy in that mix, we're going to make meeting the goal a lot easier to reach and a lot less
Hi, my name is Matthew McKinzie. How's the audio? Can you hear me? Okay, great. I want to thank the conference organizers for providing me a way to make my presentation. Oh, I see we're going to have a webcam option. Okay, great. I'm a nuclear physicist. I work for the Natural Resources Defense Council in Washington, D.C. I have worked on nuclear energy issues for quite a few years now, and I should say that NRDC's perspective is not an anti-nuclear perspective. Really, we're pro-environment, but there's an important pragmatic question about what are the best tools to use to address the climate change problem, and how can we rely on nuclear? Should we rely on nuclear to deliver some of the energy policy values that we want? Just a little more background. This past November, I testified before the Senate at a hearing on the future of nuclear power, and I'll present today some of the findings that I prepared for my testimony. Slide 2, please. Now, the thesis for this presentation is that nuclear power has some long-standing, very tough problems that Mike did a great job presenting earlier. You can hold them in your hand. There's 5. If I could ask you to think about nuclear and its problems, there are 5. Economics, safety, security, which I see as distinct from safety. I'll get into that. The nuclear weapons proliferation problem, and radioactive waste. Now, nuclear technology, nuclear reactions and radiation, they're utilized for some core capabilities in medicine, nuclear medicine, space programs, deep space, power supplies, and of course national defense, nuclear propulsion for submarines and sea vessels, and of course the awesome destructive power of nuclear weapons that our society has to cope with. But I believe that one should have a deep skepticism that nuclear power can be key to a decarbonized future, can continue to deliver energy values into the future, and have an enduring role as part of an energy policy that addresses climate change. So let me get into a few of these areas. Next slide, please. So as I mentioned, there are 5 main challenges. Recent events, even since my testimony in the Senate in November, have reinforced some of the scope of some of these challenges. And then at the very end of the presentation, I want to get into nuclear power's uncertain future, the issue of advanced nuclear and what that could bring to the table. Next slide, please. So in terms of the economic challenges for nuclear power, Mike reviewed some of this, but some key takeaways are that really the dominant contributor to cost problems for nuclear are the capital cost issues. Cost escalation during the duration of the project, high cost surprise, and a trend for the increasing capital cost over subsequent reactor builds, what's sometimes called negative learning. And in terms of understanding nuclear's contribution to climate change, a cost-benefit calculation for nuclear is difficult and complicated, because do you factor into the cost of nuclear these special externalities, uranium mining, the cost, the risk and cost of severe nuclear accidents, the whole radioactive waste issue, the cost associated with nuclear weapons proliferation, dealing with that. So these special externalities to nuclear energy really complicate that cost-benefit analysis of how nuclear compares to other technologies to mitigate climate change. Next slide, please. So I feel that NRDC works in a very pragmatic way on these issues. So I was part of the team here working on the Diablo Canyon joint proposal, which is about the closure of the Diablo Canyon reactor in 9 years. My belief is that this Diablo Canyon reactors would have closed early and suddenly, as the San Onofre reactors did, without a structure like this joint proposal, and that relates to some of the water, cooling water issues for Diablo Canyon. But the Diablo Canyon joint proposal, I feel, is a very strong planning framework for closing those 2 reactors over 9 years. It includes zero carbon replacement generation, which was not the case for San Onofre, as well as lower costs to ratepayers, grid stability, plant workforce employment, and the joint proposal does address decommissioning and spent fuel. Now, the Indian Point closure agreement, which I also was part of the team working on here at NRDC, ends litigation over relicensing that created a lot of uncertainty for energy policy in New York State. It's a commitment to plant closure in 4 years, and I would say, importantly, it's within this context of New York's 50% by 2030 commitment to renewable energy. So here are 2 situations where nuclear reactors, I think their closure is inevitable, clearly, but may be sudden and unplanned. And so we have an opportunity to address climate change and other important issues in these closure agreements. Slide 6, next slide, please. The Illinois and New York nuclear subsidies were also mentioned. I think here is also a chance to look at energy policy as a whole. There were 2 paths to this. In Illinois, it was state legislation. In New York, it was Public Service Commission orders. But I should say this was an interesting energy policy in that it was kind of a pairing of efficiency and renewables with nuclear plant subsidies. In Illinois, it was explicit. In New York, it was in parallel. The nuclear subsidies were tied to the social cost of carbon. But I should point out that in both Illinois and New York, these nuclear subsidies are the subject of court challenges, essentially whether or not FERC has the jurisdiction to decide such energy policy matters. So the economics of nuclear are extremely challenging, even for fully capitalized operating plants, challenging with respect to alternatives. And at the state level, some state policy makers are working to see whether nuclear subsidies do or do not contribute to the economy and to the climate. It's sort of a case-by-case issue. For Pennsylvania, I believe this will all be more complicated by the fact that these five plants have 3 separate owners, and what will be the negotiation for Pennsylvania? How will it impact Pennsylvania's progress on clean energy, on renewables and efficiency, to have some subsidy for its nuclear generation? Okay, so that was a bit about economics. In terms of state level act, I should say that in general there are some sort of titanic financial shifts in nuclear energy, very much in the negative direction. Often I hear the question, why can't the U.S. be more like France, have a majority share of electricity from nuclear? Areva and EDF are real cautionary tales about what can go very wrong. Areva, the nuclear giant, is technically bankrupt with billions in losses many years in a row. Standard & Poor's have downgraded Areva shares to BB minus, to junk status. Next slide, please. A similar story for EDF, Electricité de France, and the time frame on this slide is really it starts in about 2006 on the left. So this is when the nuclear renaissance was touted, when a number of companies made new investments in nuclear energy. There were supposed to be dozens and dozens of new nuclear builds in the United States. But in the end, this nuclear renaissance really resulted in some massive financial losses for Areva, EDF, and next slide, please, Toshiba. So Toshiba, as many of you have seen in the news, invested big in nuclear around 2006, acquiring Westinghouse. And it seems that this nuclear investment really may have sunk a venerable company, a venerable Japanese company. And the Pittsburgh Post-Gazette, even just this morning, had an article about restructuring at Westinghouse, downsizing. I mean, this is really a grim time for the nuclear industry. Okay, so that touched on economics. Next slide is on nuclear reactor safety. I suppose it may seem like it goes without saying, but what makes nuclear power different from other industries is this possibility that a major accident could release large amounts of radioactivity. The consequences are loss of life, also environmental contamination, the necessity to create evacuation zones, and cost. Nuclear accidents are incredibly costly. So just to give you a sense of it, in general, nuclear safety or the risk of an accident is quantified by the frequency of core damage in terms of reactor years. So one reactor operating 1 year, what is the chance that there could be a core damage, release of radioactivity to the environment? Well, all of human experience on the operation of nuclear reactors is about 17,000 reactor years. And as Mike also mentioned, we've had three core damage events. Fukushima, there were 3 meltdowns. You may count that as 1 or 3 for this kind of probability assessment. But in general, it looks like the frequency of core damage from historical experience is on the order of 1 in 10,000. So what does that mean? For a fleet of 100 reactors, you'd expect about 1 core damage, 1 severe accident every century or less. I was recently at an event at the Hart Senate Office Building in which Dr. Andrew Kadak, he's the president of the American Nuclear Society, he was telling the nuclear professionals in the audience, we have to get better at communicating the risks of radiation exposure. Why? Because there will be a next nuclear accident. And when he made that statement, he was referring to this kind of core damage frequency, that the probability of a severe accident is small but non-zero. Can society tolerate a severe nuclear accident every 20 years, every 30 years, or if it's less frequent? Well, that's a tough call. But the nuclear engineering professional, really, the sense is that you can't get the risk much lower than it is now, because the way nuclear reactors are designed call on safety equipment and call on personnel to use that equipment to perform these critical functions during an emergency. So when Amber talked about safety, passive safety, nuclear engineering is attempting to move in that direction to lower the risk of severe nuclear accident below what it is today. Next slide, please. Nuclear plant security I see as distinct from safety. The risk of an accident is if everyone at the plant, everyone who has access to the plant has good intentions. But nuclear plant security is about the case where there's either an external threat or an insider threat, and how you protect the plant and the radioactive material in the plant from that threat. Mm-hmm. The current approach in the U.S. is one of guards, guns, and gates, supplemented by intelligence, counterintelligence. But there are some real concerns about this, the security of nuclear plants, and how you measure that and how you determine that to be adequate. And one new looming issue on the horizon for nuclear plants is cybersecurity. And a lot of nuclear plants, when you see a picture of the control rooms, it sort of looks like it looks very retro. Many of the controls are analog controls because the nuclear plants were built so many years ago. But if new nuclear reactor designs are built, those digital controls would would logically be more vulnerable to cybersecurity issues. And finally, security, to my mind, also involves issues around nuclear power plants and warfare. We saw this emerge a little bit in Ukraine, in the violence in Ukraine, which was steadily approaching the Chernobyl nuclear plant. But I know that defense analysts, for example, in South Korea, worry about what would happen if a South Korean nuclear plant was attacked by North Korea in time of war. So these are all very tough issues. A nuclear power plant at spent fuel pool is a source of radioactivity that would have to be protected from terrorists or in the course of war. Next slide, 12, please. The fourth challenge for nuclear weapons proliferation, I'll just say it's a tough subject to describe quickly, but I'll just say there are two routes to nuclear weapons: highly enriched uranium, so that deals with the front end of the nuclear fuel cycle, uranium enrichment, and plutonium, which is the back end of the nuclear fuel cycle, reprocessing. Those are two routes to nuclear weapons, and in general, civilian and military technology is overlaps in many places. And so right now we have a vast and complex global nuclear nonproliferation regime, and that regime can try to manage the risk of proliferation, but can't fully eliminate that risk. And in an international structure where trust is on the decline, international trust is becoming more and more scarce, the nonproliferation regime suffers as a result. Slide 13, the fifth challenge for nuclear energy, the nuclear waste problem. The United States alone has produced just a vast amount of nuclear waste largely stored at reactor sites in wet storage, which is particularly vulnerable to the consequences of accident or threats in terms of the amount of radioactivity outside containment. This is a really tough problem. My feeling is that it's clear Yucca Mountain project is not viable, even with a Congress that would support it. The Yucca Mountain project is just too troubled and too challenged in many ways. We need to start again with a consent-based siting process for nuclear waste, and it's just a really tough problem that's decades and decades old. Next slide, please. Now, my presentation briefly touched on these 5 challenges for nuclear energy. What is the future? I agree with Mike. It's uncertain. The AP1000 reactors in the U.S. Southeast over budget, behind schedule. Next slide, please. The small modular reactor, the NuScale company just submitted its license application to the NRC, still to be reviewed, are very basic questions about plant security, plant staffing, the evacuation planning zone size. Next slide, please. And with respect to other advanced nuclear designs, I would say that transatomic, which I think I saw on Mike's slide, I saw this logo, it really is a cautionary tale here, because many of these advanced nuclear designs are really some modeling work that's been done, a PowerPoint slide deck, a pamphlet type description, but not a lot of hard analysis of the physics behind them. And Transatomic was an MIT technology startup that made a lot of claims about fuel utilization, that it would utilize fuel 75 times more efficiently and burn nuclear waste. And none of this was true. They had made fundamental errors in their calculation. It was really tough for MIT nuclear engineering. Their credibility was on the line. So advanced nuclear really has to be considered with a lot of caution. Most of these designs just haven't been. These designs haven't been prototyped. They haven't been explored. To rely on them for a solution to climate change is really premature. So the next slide, just to conclude, I've tried to rapidly present these 5 challenges for nuclear. I'll just point out that there are deep decarbonization studies, serious studies that have shown pathways to deep decarbonization that rely primarily on efficiency, renewables, vehicle electrification, and a new grid, not relying in a primary way on nuclear. And when you look at the cost, the risk, the unsolved problems, the uncertainty over advanced nuclear, you just have to compare that to ready alternatives when you really are in a resource-constrained energy policy that can address climate change. Thank you.
I really appreciate the talks. It looks like we got a lot of information, so we should be able to, understand this area more fully. It seems like timing was not well. It was talked about in issues related to how fast we might lose the plants, but even in the Pennsylvania context, where we, if we could keep plants open and we would want to build some more, is there a timing issue related to being able to construct new plants, especially if we have a number of these plants coming up to their 60-year end of life and potentially can't get a license for 80-year extension, and we have to do something? Do we need to make decisions now? Do we need to can we wait for a while, or what? Anybody that it's a free-for-all.
I'll start. I kind of skipped over it a bit on my slide, but I think I had on there it was about 2030 to 2047 that the timeline for the current 9 plants would start aging out at 60 years in Pennsylvania. The cautionary tale is that the licensing for Summer and Vogtle I think started in about the 2006 timeframe, 2006, 2007, and they're not looking to go online until sometime around 2018, 2019. So if you think that it's about 16 years till the first of these plants starts hitting its 60-year lifespan here in the state, then unless they extend to an 80-year licensing, then you have to start making those decisions so that in about 5 or 6 years from now, you'd have the license submission in so you could start building. That'd be a rough estimate. Now, whether or not there's more details behind that, I don't study Pennsylvania in particular, but that'd be my initial estimate.
Okay. Question?
Yeah, Bobby McKinzie from Ballard Spar. Yeah, I have a few questions which I'll try to quickly string together. One, one of the things I didn't hear you mention was both the potential for new technologies to extend life and nuclear uprates. I mean, there have been several gigawatts of expansion just due to uprates of existing plants. Peach Bottom just got a 300 megawatt uprate just last year. A lot of those were abandoned, and a lot of the plants have closed prematurely due to the low gas prices. What is the potential out there for greater use and efficiency from our existing plants? Second question relates to basically regulatory barriers. Is there a regulatory barrier from using the existing plants for combined heat and power? I've also heard in terms of regulatory impacts that very small thorium reactors are feasible, but using medical quantities of waste. But really the barrier there is primarily, I've heard, NRC regulations. I don't know whether that's true or not. And the final question is, in the deaths per megawatt hour, from coal, did that include the air pollution deaths as well, or is that, okay, yeah.
Do you want to take it? I don't want to jump on that.
First one.
For life cycle.
Uprates.
So for uprates, you're probably familiar that they've had significant uprates over the years for the existing plants. Some of that's a function of the material side, whether or not the fuels can get significantly better. And there has been some discussion about that, to my understanding, looking at several recent conferences I've been to, where there may be some potential from a material standpoint for new fuels to allow for not to get too technical here, but if you end up with a higher peak centerline temperature rating for the fuel, you might be able to uprate the reactor to operate at higher power, and therefore some of the existing plants may, with new fuels, be able to operate at a higher level and therefore do an uprate. But there are a lot of unknowns related to that. So all the probabilistic risk assessments that were done for those plants were based on certain power levels. Certainly materials tests were done for pressure vessels, et cetera, based on the existing flux levels inside the reactors, and therefore I don't know enough about whether or not those are really feasible uprates for some of those plants or not. I think that just like with the life extension to 80, that work is ongoing at the labs. About embrittlement for some of those from the core materials, things like that, to me, are not necessarily going to be a universal solution that will work for every plant. Some of the newer ones might be able to, some of the others may not, and that'll be probably on a case-by-case basis, both from a material standpoint, fuel standpoint, and probably certainly from a business standpoint. Whatever the local marginal pricing is for the particular plant, they may not be able to want to spend the money for the uprate for the material changes that might be needed.
I'll try to fill in the blanks. I think the other question you asked was whether or not extending nuclear operation to provide for industrial applications, whether or not that would require additional licensing approvals. And I don't know for sure, but I assume the answer is yes. I think any change in operations of our existing units is going to require some adjustment of the existing operator license. So yes, that is definitely sort of an administrative barrier that we would need to address. I think you also asked about thorium reactors and was it licensing? But I just think generally current licensing experience isn't with thorium fuel. So I think that would definitely be another area where we would need to build up more experience and knowledge, but maybe Mike would like to address that question as well.
Matt had wanted to address
If
that.
Matt, wants to, Matt's probably well. I was going to say is Matt's probably a good guy for that one. Matt?
Hey, it's Matthew. Thank you. I wanted to respond on the NRC licensing aspect to the question. So I've heard a number of claims that if it wasn't for the Nuclear Regulatory Commission's licensing process, advanced nuclear could take off like a rocket. And I just have to push back on that and say that really the issue is that advanced nuclear designs like transatomic and others, they're just so, from an engineering perspective, they're so far from being ready for the license application stage that it's really a distraction to look at the NRC as something that would cause a delay. The NuScale SMR, like I said, just submitted its license application to the NRC, which committed to a 40-month process. But preparing for that stage, NuScale and Fluor, its parent company, they were supported, financially supported by the U.S. government, by the Department of Energy, to get to that stage. So it's a big step for a company to take a conceptual design and have it ready for licensing, and that's the hurdle for advanced nuclear. Thank you.
And I would just echo what Matt said, which is that we did in part of our interviews we did last year, we expected to hear from industry and a number of others that maybe the NRC was a roadblock. The answer came back very loud and clear that they were not. They were doing what we would expect them to do. They weren't going to spend their time on designs that were not ready to submit a license application to them, and until they are, they're not going to expend a lot of money, most of which comes from industry and from the utilities, on something like figuring out the licensing and regulatory side for an advanced design, which they don't know which one will end up being feasible, whether it's molten salt or high temperature gas or whatever. On the thorium issue, I think the other issue that maybe aside from the regulatory side, which I think they could also figure out at some point, is why. Steve Brick mentioned you need to have a business case for that. Why would you develop an entirely new fuel cycle If you're going to do nuclear, you already have a uranium fuel cycle. Thorium does not really have a fuel cycle right now. There are people that want to have a thorium plant, but that involves having a production, mining, fuel form, that kind of thing. And that's, right now, I've not seen any business case that says that that's necessary at this point.
Do we have any additional questions?
Hi, Christina Simeone for the University of Pennsylvania. So my question is more of a policy question than a technology question. I believe Illinois and New York are wrestling with this a little bit, and it's relevant for Pennsylvania. In a state that doesn't have a history of supporting carbon pricing or carbon policies, for example, in Pennsylvania we have an alternative portfolio standard, but it's a mix of high and low carbon resources. When you think about something like a zero emission credit program, how have you run into experiences in these other states where certain resources, zero carbon resources, get a credit, but other zero carbon resources don't get a credit? I think in New York, the hydropower folks were a little concerned about New York's program. So it's more kind of like policy equity, not whether we should do it for nuclear, but whether it should be done kind of more broad-based or very narrowly focused. Sorry.
Well, I guess I'll just give first a more general answer, which is I think that in most cases we should be developing technology neutral policies that value low carbon generation. I think this is sort of a long-term rule. But I do think that there are some special cases, with New York and Illinois being a very good example, where there were some specific technologies that needed some more direct assistance. So I guess the answer is both yes and no. Yeah.
Matthew wanted to respond as well. I did it.
Hey, this is Matthew. I'll just be very quick. I know time is tight. So the Nuclear Energy Institute, the Nuclear Industry Trade Group, while it acknowledged what happened in New York and Illinois as beneficial to the industry, it said that's not our long-term strategy. A state-by-state approach can't work. What we want, our approach needs to be at the federal level, and the fix probably has to occur at FERC. So I don't know how, whether we'll see a lot more of these state-level energy policy going forward that include nuclear or not. But in general, if the energy policy at the state level puts requirements on what generators or what technologies can apply and receive these zero emission credits, that's often a very complex negotiation among many parties. But the requirements can be quite broad and quite restrictive from our experience, and still fly.
Okay. I have some additional questions over here. I think we can do at least one, maybe two. Yeah, we'll sneak two in. So.
Whoa. That was loud. Dave Grossman, Greenlight. I'm going to basically ask my same question I asked last time. The political reality question. So I was actually a couple of weeks ago at the excellent Advanced Nuclear Summit that Third Way put on in DC. It was very informative, but a lot of the feedback from speakers there was the national labs are great. We need to give them more funding to do advanced nuclear work, and NRC role is going to be vital. We need to give them more funding to do their thing, and there's bipartisan support for nuclear. But I don't believe we're in a bipartisan support for more federal funding for anything, maybe military, maybe not. So my question again goes back to sort of how do political realities affect the viability of technologies? If we're going to go on this deep decarb pathway and nuclear is vital, whether uprates for existing plants and new technologies, advanced designs, if the role of the labs, if the NRC, if all these things are vital, well, I guess how vital are they? And if there isn't actually going to be increased federal funding for these things, are there other pathways where these things can actually come to fruition and play the role you're envisioning for them?
Wow, that's a tough question. So, I guess there are a lot of pieces to the puzzle right now. Achieving deep decarbonization is going to require long-term policy goals, both at the federal and at the state level. Achieving deep decarbonization is also going to require progress and innovation. And I honestly don't know sort of the portion of innovation that is developed at the federal versus the state level, but I suspect that this is primarily something that's driven by the federal level, and that this is really going to be a critical piece of the puzzle moving forward. So, this is going to be sort of a big focus of our energies the next 4 years, trying to keep that part of the puzzle intact and to keep it growing. That said, we think that 4 years is a short time in the scope of the decarbonization challenge, and we need to, there's opportunity for the states to keep things moving forward in terms of policy, and we need to just sort of keep our sights set at being ready to get things rolling again when the time is right. So.
We have one more question over here, and that'll be our last one.
Okay, and this is a short one. Nuclear right now is mostly running in baseload mode, where it just turns on and turns off a year later. But the future is going to involve some sort of cooperation between nuclear and renewables. And so you're going to be throttling nuclear plants up and down on a daily basis. Does that run into any technical or regulatory limitations?
Well, regulatory, not that I'm aware of significantly, because there are some that can ramp now. Some of it's technical in that they're certainly not designed that way, nor is it a business case that a lot of the utilities would want to run them at, because if they're not running it at peak capacity, then they're not earning them the maximum amount of money. So, but in the future, I agree with you. One of the things you want is to have that load following capability where you can perhaps have it blended with a system that will allow you to, let's say, produce water or chemical production or something like it that allow you in a newer design to ramp the plant up to a full capacity, but be changing where that output goes. Some of it to electricity, some of it to other potential loads, whether they're process heat loads or otherwise. So the current plants, that's a little more challenging. Some of them can. My background coming from military nuclear is that that's how we operated all the time. We always ramped. And so you always have the ability to go up and down, but your plant has to be designed from a safety standpoint, from a plant configuration standpoint to do that. Some can do that, some are not as easily done, and certainly the business case is the most challenging thing, I think, because even if they can, they may not want to because they're already challenged operationally to make their money back from an operating cost standpoint if they're ramping. So that's one of the biggest hurdles. I think will be a business hurdle.
Okay, Matt gets the final response here.
Okay, I think I'm unmuted. Thank you so much. On that issue of baseload and load following, I find that a very interesting subject. And one of the things I've heard about the NuScale SMR is that because a NuScale SMR nuclear plant consists of maybe 12 modules, it could perform load following in a way that our current nuclear plants can't. But it's also interesting to consider why PG&E in the Diablo Canyon case thought that the large baseload of the nuclear plants was a liability in the future. They're already seeing sometimes up to 30% renewables on the grid on a bright sunny morning, and that big baseload just pushes those renewables out. How do the grid operators adapt to renewable generation at 30%, 50% or more in very creative and interesting ways? More sensors on the grid, so you know what the voltage is and generation is, and also better weather models. So from our perspective at NRDC, baseload is a concept receding in the past, and one more challenge for nuclear energy in the future.
Okay, thanks, everybody. I appreciate the speakers. They gave us some really good information here, and I appreciate your attention, especially in that glucose high after lunch.